Hey, how's it going? Good. I started when I started water. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. You see daylight again? Well, kind of. We see light, no sun because it's been raining like crazy. But yeah, hopefully everyone's staying dry. Hopefully everyone's staying safe. I know there's a lot of flooding going out there, so make sure you guys are staying dry. Okay, so today the plan for today is we're going to continue on with our lecture notes on unsteady equations. And today we're moving to 2D. And so today is going to be fun. Well, I guess depends on what your definition of fun is. So, we're going to be, there's going to be a lot of terms, there's going to be a lot of indices. And so, it's going to be very easy, I think, to kind of lose track of kind of where you are. But, I'm going to do my best to kind of go through every step so you can see everything step by step. And, hopefully what you'll see and hopefully what you'll feel is that, what we're going to do today is just kind of the application of basically the same thing we've been doing, for the last couple lectures. It's just that, there's just some extra terms for 2 dimensions, okay? And then, that second dimension, of course, is going to add more indices to keep track of, but, it's the same idea. All right, so remember homework 4 is out there. So remember homework 4 is due not this Sunday, but the following Sunday. And actually after today, you should be able to do most of it. And then after today, we'll have maybe one more, maybe a half a lecture more for time marching schemes that we'll cover next Monday. And then after that, you'll definitely have everything you need to do for homework 4. Okay. And of course, after next week is going to be spring break. And so, I'm looking forward to it probably as much as you guys. So, I want to make sure we finish up all the time marching stuff before that. Okay. I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So let's talk about unsteady problems in 2D. So something in the chat, let's see. Graduate project. Oh, yes. So if you're a graduate student in this class, or you're taking this course for graduate credit, there is an extra assignment that you have to do in order to get graduate credit. We'll talk about that after spring break. So after spring break, I'll introduce the final project, which you guys are going to be doing for that. And so if you're a graduate student, there's an extra component to the final project that you have to do. So that's kind of the extra thing. So it's not an extra assignment. It's just kind of more coding. Essentially, you have to write more code than the undergrads. Okay. So let's talk about unsteady convection diffusion in 2D. So today, we're going to be solving the entire equations. Okay. So this is as big as the equation that we're going to get. Okay. So let me write out the differential equation form first. So just like always, we're going to start with this, and then we're going to take each term and then apply finite differences to it. So just like we normally do. So partial phi, partial t, plus u partial phi, partial x, plus v partial phi, partial y is equal to k partial squared phi, partial x squared, partial squared phi, partial y squared, plus q of x, y, okay? So this is the whole shebang. So every term here is accounted for. So we have our unsteady derivative here, partial phi, partial t, and we have the convection terms, both the x and y convection terms, as well as the diffusion terms, x and y diffusion terms. And of course, we have our source, okay? Okay, so let's take this, and then we're going to replace all the derivatives with finite differences, okay? All right, so let's start with the time derivative. And so for the time derivative, remember, we're doing our normal, technically it's, I guess it's a forward difference in time. Okay. So phi n plus 1 minus phi at n superscript, all divided by delta t, okay? And since we're in 2D, we have to have the I and j coordinates as well. So it's going to be I comma j and I comma j, okay? So this is our time derivative here. So this term became this term. Okay, then we have our convection terms. And so just like I did in 1D, I'm going to assume we can use central difference here just to make it convenient, because we don't know what direction u and v are going. So I'm just going to use central difference. Okay. And so for the x velocity, we have u, v, I plus 1, comma j, minus phi I minus 1, comma j, divided by 2 delta x. Okay. So this term became this term. Okay. Then we have our y derivative, so same thing. So we have plus v, phi I j plus 1 minus phi I j minus 1 all over 2 delta y. Okay. This term became this term. Okay. Using colors here just to kind of indicate, where they're coming from, just because the finite difference form is going to be a lot longer because we have, the finite difference expressions are much bigger than the derivatives. So I want to make sure that you kind of know, where each term is coming from. Okay, then we have our diffusion terms. So this, we're going to use our normal central difference. And so we have phi I plus 1, j, minus 2 phi I, comma j, plus phi I minus 1, comma j, for delta x squared. Okay. This term came from the second order derivative in x. Okay, using green for that. So to this, we're going to add our second order derivative in y. And so that's going to be phi I j plus 1 minus 2 phi I, comma j, plus phi I j minus 1 all over delta y squared. This came from this. Okay. Finally, the last thing is just our source term. So I say q of xi, comma y j. Okay. A lot of stuff going on. So, more finite difference than probably you ever want to see in one place. Okay. All right. So of course, these are things that we've done before. And so we've done 2D problems. And so we've seen a similar equation to this. Of course, the big difference here is that, since we are at an unsteady case, for all the phi terms that don't have a time index associated with them, we have to assign either n or n plus 1. Okay. And so for all phi terms that do not have a time index, we're going to assign an n or an n plus 1. Okay, so just like we did in 1D, except now there's a bajillion more terms because we're in 2D. Okay. And so of course, this choice, this choice of either n or n plus 1, that leads us to our two methods. And so if we assign n to everything, this leads to explicit Euler. Okay. And then if we do n plus 1, this leads us to implicit Euler. Okay. And last time we met on Monday, we talked about the difference between explicit and implicit. Okay, so those differences are still going to apply here as well. All right. So just like I did in 1D, we're going to start with an explicit method, okay, just because it's a little bit easier to set up. And so for all the phi terms here, I'm going to assign a time index of n. So for this x convection derivative, I'm going to assign an index of n, okay, n. Then for the y convection derivative, n. For the x diffusion, we have n. And then for the y diffusion, we have n. Okay. We have like alphabet soup going on here. So, I's and J's and N's all over the place. Okay. So all that is looking good. And so our next step is going to be algebra. And so we're going to take this expression here and we're going to group the like terms. And we're going to sort the terms on either one side or the other in order to get an expression which has basically coefficients. So that's basically what we like to do. Okay. So next terms. Put n plus 1 on left-hand side and n on right-hand side. Okay. And we're also going to multiply by delta t. Okay. Just so that we don't have to deal with that 1 over delta t over there. Okay. Because remember, our goal is to basically manipulate this expression so that we have an equation that we can solve, an explicit equation that we can solve for phi n plus 1. Okay. And so now we need to do the algebra in order to get that. Okay. Any questions on that, on anything we've done so far? Okay. All right. So let's go ahead and do that. So first, let me go ahead and multiply by delta t and move the terms around. Okay. And so if we multiply by delta t and we take the convection terms and we take this phi n term and move it to the right-hand side, we end up with the following. Okay. So I'm kind of doing more than one step at once here, but hopefully it's not too hard to follow. Okay. And so on the left-hand side of the equation, we're left with phi I comma j at n plus 1. Okay. Remember, for explicit we should have only one n plus 1 term in our equation, and that's what we solve for eventually, essentially. Okay. And then on the right-hand side, what we're going to have is a positive phi I comma j at n. Okay, because that came from the time derivative term, and we have all of the convection and diffusion terms. So we have minus u delta t divided by 2 delta x. It's phi I plus 1 comma j at n minus phi I minus 1 comma j at n. Okay. This v delta t divided by 2 delta y times phi I j plus 1 at n minus phi I j minus 1 at n. Plus a delta t divided by delta x squared times phi I plus 1 comma j at n minus 2 phi I comma j at n plus phi I minus 1 comma j at n. Okay. Okay, then we have the y diffusion term, so that's phi I j plus 1 at n minus 2 phi I comma j at n plus phi I minus 1 comma j at n. And then we have our source term q at xi yj multiplied by delta t. All right, so we have a mess, okay? Whenever it takes more than one line to write an equation, you're kind of in for it. But the fact that it takes 2.5 lines to write this equation, means that it's really, there's a lot of stuff going on. Yeah, so definitely take your time. So, when you're writing this equation, make sure you get all the positives and negatives and the coefficient values correct. you know, there's a lot of details in this equation. Okay. Yeah. Oh, thank you. Yeah, see, not even following my own advice. I'm not being careful myself. Thank you. Yeah, so that last one should be I comma j minus 1. Mm-hmm. Okay, so we're almost there. And so the last step here is just to group the like terms, because what we want to do is we want to take all of our phi terms here, okay, and get a single coefficient for each term. Okay, so we're just going to be doing some grouping now. Okay? This is the last step, I promise. And so after this, we'll box the equation. Okay, so we have phi I comma j n plus 1 is equal to, right? We have u delta t divided by 2 delta x plus k delta t divided by delta x squared times phi I minus 1 comma j at n, okay, plus minus u delta t divided by 2 delta x plus k delta t divided by delta x squared phi plus 1 comma j. And we have the y, the bottom neighbor and the top neighbor. So the bottom neighbor term is v delta t, 2 delta y, a delta t divided by delta y squared, I comma j minus 1 at n, plus minus v delta t divided by 2 delta y plus delta t over delta y squared, v I comma j plus 1 at n, plus minus 2k delta t divided by delta x squared minus 2k delta t over delta y squared plus 1. Vi comma j at n plus q at xi comma yj delta t. Okay. So I wrote a little bit smaller to get it into 2 lines. All right, so this equation right here, this is our explicit Euler time advancement for 2D problems. Okay. So remember, you know, we like to put our equations in this form because they give us the coefficients for the phis, right? And so whenever we're in 2D, you know, we have 5 phi terms that we're concerned with. So we have, you know, the center node, we have the left neighbor, we have the right neighbor, we have the bottom neighbor, and the top neighbor. Okay. And so I formatted this equation to give us those exact coefficients. Okay? Because what we're going to do, and so after this, I'll show you the code, is that you'll see that we're going to take these coefficients here. just like we did in the steady problems, those coefficients are going to go into a matrix. Okay? And so the kind of the good thing about 2D problems is that they're so, you know, they're so complex that you almost never do these by hand. I would certainly never ask you to do an unsteady 2D problem by hand. And so, you know, when you see expressions like this, you know, and you see kind of these equations that we have for the coefficients, you know, just think about those as inputting those directly into code. Okay, and you'll see that in the code very, very soon. Okay. Any questions on this? Okay. And so once again, you know, because we have an explicit method, you know, our what we're going to end up with is something like this. And so for explicit methods, our time advancement remember, the hallmark of explicit time advancement is that we don't need to do any matrix inversion. We don't need to do any linear solve. We just do matrix vector multiplication, okay? Where the coefficients of this matrix here, this A matrix, are going to be given by the terms that I've circled above, okay? And then this B vector right here, remember this, the values of this B vector usually come from boundary conditions, or they come from any kind of source in term. Okay? So this right here is just matrix vector multiplication. Remember, matrix vector multiplication, when you do it in code, is extremely cheap, okay? And so explicit methods, each time step, you know, we're not really expending much cost at all. Okay? The downside to explicit methods is that you might get an unstable solution if your time step size isn't small. Okay, so remember, that's kind of the main trade-off between the two. Okay? But for now, the example that we're doing, it is stable. I'm pretty sure it's stable. And so we don't have to worry about that, but you know, that's always one thing you have to look out for explicit methods. Okay. All right, so let's do an example. Let me set up the problem here, you know, in writing first, and then we'll jump into the code after that. Okay, so we have our domain. So we have a two-dimensional domain here. We're going to assume Lx and Ly are the same. Lx and Ly be 1, so we have basically a square domain with a length of 1 in each direction. We're going to assume we have 30 nodes in each direction as well. So both Nx and Ny are going to be 30. Okay. To keep things simple, let me put Dirichlet boundary conditions all around. And so we have phi is equal to 50 up top, phi is equal to 50 on the left, phi is equal to 25 on the right, phi is equal to 25 on the bottom. Okay, so, you know, Dirichlet boundary conditions all around. So we don't have to worry about any kind of difference. Okay? And the equation that we want to solve looks like this. We have partial phi, partial t, plus 50, partial phi, partial x, plus partial phi, partial y is equal to 3 partial squared phi, partial x squared, plus partial squared phi, partial y squared, plus q of x comma. Oh, sorry, we have a q here. The Q here is 3xy. I think we've solved this problem before, except this time we're going to do it in an unsteady fashion. Okay. So first thing I want to do, before we jump into code is let's define all the parameters for this problem. Okay. So first, we're just reading off this equation here. We can see that u is equal to 50. Bless you. Okay. So u is our x velocity. So that's the coefficient that's in front of partial phi partial x. Okay. V here is equal to 1 because that's the coefficient in front of partial phi partial y. A is equal to 3. So those are all values we're going to put into the code. Right, then we have our grid spacing. So it's delta x, delta y. So delta x, delta y here is going to be 1 divided by 30 minus 1. Okay. So that's going to be some weird decimal, but we're going to let the code compute that for us. But it's good to have the expression for us here. Okay. Next is our time step size, and so this is going to be given to us. And so just to make sure that we have a stable solution, we're going to set our time step size to 0.0001 seconds. So that's 0.1 milliseconds. And the number of time steps that we want to solve this solution for is 250. Okay. Okay. And so make sure you have this problem down because once I switch the code, it's going to be hard to kind of come back to this. Okay. But basically what we're going to do, or kind of our strategy here, is to first of all, at the top of the code, make sure that we have all these parameters set as they are. Okay, so we're going to make sure our velocity is set correctly, our diffusion constant is set correctly, our grid spacing, our time step size, all those is set the way we want. Okay, and then after that, we're going to go into the code, and I'll talk about kind of the structure that you're going to see. Okay. All right. Any questions on this? Okay. All right. So our question, is it 30 minus 1? Yes, it's 30 minus 1. Because remember, to compute the grid spacing, it's nx or ny minus 1. Yeah. Mm-hmm. Okay, so let me go ahead and share. And I forgot to download the code, unless I downloaded it on Monday. Let's see. Oh, I did download it on Monday. Good. We don't have to log into the portal, and you guys don't have to see that I still haven't done the Title IX training. Okay. All right. So can everyone see the code? Font size is looking okay. Okay. All right. So let's check section 1. So remember, the way I structure this code is, section 1. That's where we define all of our variables. Okay. So we have LX, LY. So, both of those are set to 1, just as the problem dictated. NX, NY, those are 30. Okay. We compute the total number of nodes. So the total number of nodes here is NX times NY. Okay. We have the grid spacing dx, dy. So that's LX divided by NX minus 1, LY over NY minus 1. Okay. We have the diffusion constant, VISC, which is 3. The X velocity is 50. The Y velocity is 1. Delta T, our time step size is 0.0001, and NT is 250. Okay. All right. So all of the parameters here are present and accounted for. Right? And so one thing you'll notice from this point on in the class, I'm going to be giving you guys basically completed codes in the course, just because these codes are a little bit too complex to kind of work on together as a class. And so I'm giving you these codes mostly in a complete state. And so when you go to do your homeworks, the coding parts of the homeworks, start with these codes. So don't write the codes from scratch, and see, which parts that you have to modify from these codes in order to make it work for your homework problems. Okay, so last thing we're going to do in section 1 here is we're going to create empty matrices and empty vectors for A and B. Okay, so we have A is equal to zeros n tote by n tote, and then B is equal to zeros n tote by 1. Okay. Okay. Any questions on this code so far? So far all we've done is just kind of define the variables. Okay. All right. So next we come to section 2. Right. So in section 2, what we're going to do is we're going to fill out the matrix A and the vector B with the proper coefficients. Okay. And so this is where our explicit Euler equation kind of comes from. Right? And so if you look back in your notes, that kind of expression that we derived at the beginning, there are 5 phi terms, right? So there's a coefficient for the left neighbor, there's a coefficient for the right neighbor, there's a coefficient for the bottom neighbor, the top neighbor, and the center neighbor. Okay. And so what you're going to see is that I'm going to be assigning these variables, okay, or these coefficients. Okay. And so first thing that we see here is that we have a loop. And so just like we normally do in 2D, we have we have a nested for loop. And so we have one for loop over the I index, one for loop over the J index. Okay. And then just like we've had it in 2D problems in the past, we have to compute all the ID numbers. And so here we have our normal ID equation. So nx times j minus 1 plus I. Okay. And then all of the modifications that come with the left neighbor, the right neighbor, the top neighbor, the bottom neighbor. Okay. And so from here we come up to the coefficients, right? And so remember there's 5 that we have to set. And so we have to set one for the left neighbor, the right neighbor, the top neighbor, the bottom neighbor, and the center node. Okay. Okay. Oh, actually, there's a typo. So this one should be minus here. Sorry about that. Okay. Okay, so let's start with the left neighbor first. And so if we look at the left neighbor here, we have the x velocity. So the x velocity is u. We multiply by delta t, and we divide it by 2 delta x. Okay, so that should match the coefficient that you have in your notes. And then we add to that k times dt, or delta t, divided by delta x squared. So divided by dx times dx. Okay. Okay. So was everyone able to see that, in your notes that this coefficient here matches, the first term in our expression? Okay. Then we come to the right neighbor. So this one, right neighbor, remember, is I plus 1. Okay. Phi I plus 1 comma j. And so that coefficient there is a minus u delta t divided by 2 delta x. Okay. So that's the first, that comes from convection there. And then we add to that k delta t divided by delta x squared, which is this one here. Okay. Okay, so then we come, so these are a little bit out of order. So now we have the up ID. So this is the fourth one that we did. So this is the j plus 1. So there's a slight typo in the code that I posted. So I'll post an updated one after the class today. And so if you look at the j plus 1 coefficient, it's a minus v times delta t, okay, divided by 2 delta y. Okay. And then we add the diffusion term, which is the plus k delta t divided by delta y squared. Okay. Right. And then we have the bottom, ID. So this is j minus 1. Okay. And so j minus 1, we have a positive v delta t divided by 2 delta y plus k delta t divided by delta y squared. Okay, so that should match up with the third term that we have in our explicit Euler equation. And then finally, we have the center node. So that's my ID comma my ID. And so that is a minus 2k times delta t divided by delta x squared minus 2k delta t divided by delta y squared plus 1. Okay, so that's the fifth term in our explicit Euler equation. Okay. So was everyone able to see how these coefficients kind of match up to what we kind of wrote and we derived earlier in the class today? Yeah, so remember, the equation that we did is long, but, you're not actually, computing each of those expressions, you're just plopping them right in the code. Right? So basically word for word, or, whatever we have for our equations for the coefficients, we just put directly in the code, and we just let the code kind of solve it for us. Okay? Okay, and then finally, we have the source term. And so this is going to go into the vector B. Okay? And so for that, we need to compute the x position and y position. So this x position here, this is xi, And this y position here is yj. Okay. So these are our usual expressions for this. So for xi, we do I minus 1 times dx. And for the y position, we have j minus 1 times dy. Okay. And I don't know why I turned off the source term. And then for our source term, which is going to go in the vector b, we have 3 times xi times yj times delta t. So again, just like we have in our notes. Okay, so that's the main, I'd say that's kind of the main part of this code right here, just making sure your coefficients are correct and making sure that you add the source term correctly. Okay, so if there's kind of one part to focus on here is this part, just mostly to make sure that all these coefficients are right. Any questions on this here? Okay, all right, so that's all the interior nodes. Next, we have to set the boundary conditions. And so, for our boundary conditions here, we have all Dirichlet boundary conditions. First of all, we create a variable here for the current solution. And so our current solution we assume is going to be 0. Okay. And then we apply a boundary condition on each of the boundaries. Okay, so we have the left boundary, the top boundary, the right boundary, and the bottom boundary. Okay. And so because we have Dirichlet conditions all around, these are going to be fairly simple. Okay. And so for for the right-hand side, we're just going to, for the vector b, we're just going to set a value of 50 at the correct nodes. Okay. So just like we've done in 2D problems in the past, we are looping over all of the nodes on the boundary. Okay. And so we start with the left boundary, where we start with an I value of 1. Right. So everything on the left boundary has I is equal to 1. And so we're going to loop over j. So we say for j is equal to 1 to ny. Okay. Ny minus 1 if you don't want to double count the corners. And so we have my ID is equal to j minus 1 times nx plus 1. Okay. So this is the ID number for all of the nodes on that left boundary. Okay. Remember, for the boundaries, we have a fixed value of I in this case. And so we plug that directly into our ID equation. And then we set the b value equal to 50. Okay, and then you don't have to do this because eventually, the initial condition, the time loop will fix this. But if you want to make sure that your initial condition satisfies the boundary condition, you can set this as well. But this is optional right here, so you can comment this out if you want. Okay, right on with that. Okay, and so we're going to repeat that for all the other boundaries. And so we're going to have it for the top boundary, where for the top boundary, our fixed value here is j, so j is equal to ny. And so for our ID equation, we have nx times ny minus 1 plus I. And then we have b at my ID is equal to 50, same as before. Okay. For the right boundary, it's going to be the same. We're going to loop over j. But our fixed value here is I is equal to nx. And so we plug that into the ID equation. Okay. And then the boundary condition there is 25. And so we set those equal to 25 over there. And then for the bottom boundary, we have j is equal to 1. And so we're going to loop over I and do the same thing. Okay, so that's all the boundary condition stuff. Any questions on any of that? Okay. Okay, and so finally we get to the time margin. Okay, so this is where we actually apply the time margin. Okay. Okay. And so first thing I'm going to do is I'm going to make a vector called sol next. And so this is going to be the solution at time step n plus 1. So this is phi comma j at n plus 1. Okay. And then from there, I'm going to write a loop here to loop over all of the time indices, right? So we have 4 t step from 1 to nt, where nt, that's the number of time steps that we want to do. Okay. Don't worry about this end plot. So this end plot here is just to kind of help me with the plotting. And then here we see the main part of the explicit Euler. So the explicit Euler, remember, now that we have our matrix A, now that we have our matrix B, so we just wrote the code to kind of specify these values. And so to compute the next value, we have A times the current solution plus B. And then we update the current solution just like we always do for our unsteady problems. Okay, so this basically sets now that we solve this, we say that phi I comma j at n is equal to phi I comma j n plus 1, which is just what we saw for. Okay, and so the rest of this, don't worry about it. So this is all just for plotting, but you know, and usually I'm gonna write that code for you for the plotting just because it's a little bit complex, but you know, I want you guys to focus on this term right here. All right, so let's go ahead and run the code and see what we get. Okay, so how many, oh my goodness, we produced 25 plots. Okay. Now I expect to make so many plots. Okay. All right, so we're gonna start with figure 1, okay? Remember, this is an unsteady problem, so it's gonna be changing with time. So each of the figures that we have here is gonna be the solution at a different time, okay? So we'll start with figure 1. So this is kind of what the solution looks like at the beginning. And so at this point, you know, the only thing that we really have is that, you know, we have our boundary condition terms. And so, you know, the solutions here on the left edge on the top, those have a value of 50. And it's a little bit hard to see the bottom and the right, but these have a value of about 25, okay? Meanwhile, everything else is pretty much 0 because, you know, we haven't time advanced that much yet, okay? All right, so let's look at figure 2. Okay, and so in figure 2, let me put these kind of side by side so you can look. And so eventually what's going to happen is that because we have mostly diffusion here, you know, a lot of basically all the boundary conditions are going to propagate inwards toward the middle of the domain, okay? And so the difference here is a little bit subtle, but what you should see is that, you know, you can see that this band right here got a little bit thicker, okay? And so what you're seeing is the boundary conditions are kind of propagating towards the middle, okay? So this is after a few more time steps have gone. All right, so let's look at figure 3. And so in figure 3, you can see that it's advanced a bit more, okay, because some more time has passed. Now let's look at figure 4. Figure 4, you can see some more time has passed, and so you can see that, you know, this inner part right here it's starting to, you know, become more full, so it's not going to be 0 anymore. Figure 5. Figure 6. Remember, we have an x velocity too, and so that's why you see this growing from the left, you know, a lot faster because we have a velocity that's basically going this direction. Right? And so basically any condition or basically any heat that's being made on the left boundary is being pushed towards the middle a lot faster than top to bottom. Okay. All right. So let's look at figure 7. So we're getting warmer here. Okay. Right. Figure 8. Okay. Getting warmer. So I'm going to skip ahead just because I'm not going to do this 25 times. All right. So let's look at figure 15. Okay. So here we're getting pretty close to steady state here. And so if you compare, you know, what happened here was that, you know, the velocity pushed this boundary more towards the middle. Okay. And you can see this edge kind of forming here. So we have kind of like an S-shaped edge right here. All right. So let's skip ahead to figure 20. You can see that we've pushed forward a little bit more. Okay. One thing to be kind of aware of is that, you know, just be a little bit careful here that the color bars here are changing. Okay. And so now our minimum solution here is 25 as opposed to being 0 before, because, you know, everything is basically diffused through at this point. Okay. And then finally, let's look at the last solution. I don't think it's gonna be that different from that one though. It's gonna be a little bit different. Okay. And so this is basically what the steady state solution is looking like. All right, and so you can see here that, you know, we have kind of a nice smooth distribution for our temperature. You know, the only difference here is that we have this kind of little bump right here because of our velocity kind of pushing out that region right there. Okay. All right, and so if you wanted to, you know, you could definitely run this code and then kind of play all the images in sequence, and you'll see this kind of building up in real time. So almost like a post-it note kind of flip book. Actually, let me run it one more time. Unfortunately, I'm making the plots in reverse. And so, you know, you can see a reverse time lapse, right? And so what I'm going to do is I'm going to click on the X button here pretty rapidly, and you'll see kind of the opposite reaction kind of take place. Where this is the steady state, and then we'll kind of go backwards towards the initial conditions. Okay. All right, I'll do it one more time. Okay. So this is the final state, and so just play this animation, but play it in your mind backwards. Okay. All right, so you see that edge that's forming, so it's kind of deforming now because we're playing it in reverse. Actually, you know what? I can fix that. There's no reason why we can't do that. Let me fix this code just a little bit, just so you can see it playing in figure. Let's do 25 minus 10. Okay, let's try this and see if that works. Okay, so it just produced them backwards this time. And unfortunately, so the thing with time marching is that you can only solve them one way. And so, you can't solve it backwards. And so you can't start from the full solution and then go backwards, but But imagine this happening backwards, and it would be really cool if you do that. All right, anyway, so, in the next section of the notes, I'm actually going to have code that actually produces a video. And so we don't have to do this kind of weird, kind of flip book thing, but the point of this was not really just the animation. It was more about how we actually set these coefficients and how we actually advance forward in time. Okay, so there are a couple of typos in this code, so I will post a fixed version of it after the class. But are there any questions about this code and kind of how it's structured? Okay. All right, so you guys can definitely play around with that. Oh, question in the chat. Let's see. So this is a heat flow map, actually. Yeah. So the solution that you're seeing here is actually temperature. Yeah. And so on the left-hand side, where it's yellow, those are hotter temperatures, and where it's blue, those are cooler temperatures. Yeah. And so conceptually, what you can see is actually, let me go back to the initial conditions. And so conceptually, the way you can kind of look at it is like this. And so remember, our boundary conditions here is that we have phi is equal to 50 over here, and then 25 on the right and bottom boundaries. Okay. And so this situation here is changing with time. We didn't put any temp to represent the heat transfer, right? No T terms. So the phi here is our temperature. So our phi, this is temperature. Okay. I didn't fit it, but our phi is our temperature. So what we're viewing here is a field of phi, right? So each little pixel here, that's the phi value at that location, right? And so when what we're plotting here is basically the temperature field. Yeah. And so visually, what's happening is that we have our boundary conditions here. So we say basically the temperature is 50 on the left, it's 50 on the top, and it's 25 on the left and right boundaries. Okay. And then as the simulation goes, this temperature here, this heat is going to start diffusing towards the middle. And because we have an x velocity of 50 in the x direction, the transport in the x direction is a little bit stronger. Actually, it's a lot stronger than the y direction. Okay? So that's why in our final plot, we have kind of a thing that kind of looks like this. Okay? Where this little bump right here is due to the fact that we have a x velocity in that direction. Yeah, but what we are viewing here is a temperature field. Mm-hmm. Yeah, whenever we have our equations in the class, just think of phi as temperature. Yeah. No, phi is directly temperature. Yeah. Mm-hmm. Yeah, the derivative of phi would be heat flux. Okay, all right, so let's go ahead and bring it back to the notes. Okay. So one last thing that I wanted to cover in this section here before we move on to actual videos is implicit Euler. So the code we just wrote and the example problem we just did was for explicit Euler, right? But we can of course do the same thing for implicit Euler. And so, remember the main difference, and this comes very early in the derivation. In order to turn a method or a time marching scheme to implicit, we make sure that for all the phi terms that don't have a time index, we assign it n+1. All right, so I'm going to do that kind of really quickly here, just so that you have the equation. Okay. I don't have an example code for this yet, but in the next section I do have an example code for implicit 2D. Okay, at least I'm pretty sure I do. Okay. Okay, so I'm gonna start the derivation. Remember when we started today, we started with the full differential equation, right? The first step that we did was we replaced all the derivatives with finite difference. So I'm gonna start from that point. And so, I've already basically taken all the derivatives here and replaced them with. Okay. So that was the point of, we started from the differential equation and we just replaced all of the derivatives, right? So we have central difference for with the convection terms, central difference for the diffusion terms with second order second difference, okay? And we have our forward difference for time. Okay, so the big difference here, of course, is, we're gonna apply a time index of n+1. Okay? So for all the phi terms here that don't have a time index, we're just gonna apply n+1 to them. So just like before, what we're going to do is we're going to move all the n+1 terms to the left-hand side. All the n terms to the right-hand side. And we're going to multiply by delta t. So I'm going to skip most of the steps here just because, you know, it's mostly going to be the same algebra, same messy algebra, but I will give you the final result that you can basically use for coefficients. Okay. Okay. And so the final result. So after lots of algebra, after lots of algebra, we end up with the following expression. So we have minus u delta t divided by 2 delta x minus k delta t delta x squared vi minus 1 comma j n plus 1 plus u delta t divided by 2 delta x k delta t divided by delta x squared. For the right neighbor, phi I plus 1 comma j n plus 1 plus minus v delta t divided by 2 delta y minus k delta t divided by delta y squared. As phi I comma j minus 1 at n plus 1 plus positive v delta t divided by 2 delta y minus k delta t divided by delta y squared. As phi I comma j plus 1 n plus 1 plus 1 plus okay. All those diffusion terms at the center node. And so that's 1 plus 2k delta t divided by delta x squared plus 2k delta t divided by delta y squared times phi I comma j at n plus 1. And on the right-hand side, we only have phi at I comma j at n plus q xi yj times delta t. So this is our implicit Euler. Advancement for 2D problems. And so another doozy, so, you know, another very long expression here, but remember, you know, the way that you use this is that you basically take each of these coefficients. So these are the coefficient values here. And you're going to plug those directly in the code, right? Because remember, in the code, our main goal is to form our left-hand side matrix and our right-hand side vector, okay? And so what you're filling into that matrix is going to be exactly those terms, okay? And remember, there's no need to compute these terms yourself. You just have to take this formula and put it directly in the code and let the code compute these expressions for you. Okay. Any questions on this kind of big expression here? Probably people are still writing it down. Right. And so remember, you know, this is an implicit method, right? So implicit methods, they have, you know, this unique property, right? And so the main thing with implicit methods is that, you know, we end up with a system that looks like this. A, B, I, comma, J, n plus 1 is equal to phi I, comma, J, n plus Q, xi, yj times delta t, okay? Now, if you look at our equation, most of the terms are on the left-hand side of the equation, right? And so that is not by mistake. Okay? And so because most of the phi terms are on the left-hand side, our coefficient matrix is on the left now. Okay? And so unlike the explicit methods, we don't have an explicit equation for phi n plus 1, okay? And so in order to solve this system, we have to do matrix inversions. We have to invert our coefficient matrix, or in other words, we have to solve a linear system, okay? So just like in 1D, so whenever you have an implicit method, you have to solve a linear system to get your results. So we have sol next. For explicit, we had this. So for explicit, we have A multiplied by sol current plus B, okay? So this right here is explicit. Okay. Remember, explicit is very cheap because when you just perform a matrix multiplication, this A times sol current, that is super cheap. And you add B, that's even cheaper. Okay? But for implicit you have this. And so you have sol next is equal to A backslash B. Okay? I should probably be more precise here. So this B here, let's put parentheses. So this would be sol current plus B. Okay? So this right here, the fact that we have to do a backslash is a hallmark of an implicit method. Of course, that backslash operation there is not cheap, and so that backslash operation there is going to cost you, quite a lot of cost. Okay. Yeah, backslash is inverse. Yeah. You can actually use the inverse function in MATLAB, and so you can do inverse of A multiplied by that. But that's actually even slower. So if you use backslash, it's kind of like a smart inverse. Yeah. It's like inverse and then multiply at the same time. Mm-hmm. Okay. Any questions on this? Okay. All right. So we're kind of at an awkward time right now because we have about 10 minutes left. I kind of did want to start the next section on time marching schemes, which is for unsteady boundary conditions. But maybe we'll leave that for next time because I think anything that I cover now, I'll have to just review it on Monday anyway. So let's go ahead and call it. Go ahead and call it early today. And so if you didn't pick up your exam on Monday, I have your exams here, and so you can feel free to pick it up. If not, thank you guys for coming in today. I know it's been kind of raining a lot, so I appreciate you guys coming out. And so stay safe, everyone. Stay dry. Hope everyone has a good weekend, and I will see you on Monday. Question: wouldn't it be easier to solve for the term with n for implicit? So remember, the solution at n, we already know that, and so that's a solution at the current time step. And so that's something that you already have knowledge of, either from the initial conditions or from the previous time step. And so what you're solving for basically in every time marching scheme, whether it be explicit or implicit, is you're solving for n plus 1. So n plus 1 is the unknown in this case. Yep. You guys have a good weekend. Stay safe, guys. Stay dry.
See you tomorrow, right? Yeah. I was talking to I have a meeting at 9, but I was talking to Jerry about doing a workshop tomorrow or after the workshop. Thanks. We're great. I want to start. I was gonna start tomorrow. So yes, I started, but that's it. Wait, did you post a reading? Yeah, that like 2 weeks ago.
Hey, Justin, have a good weekend. Hey, Ozzy.
Class students?
Yep, another class.
What class?
540. It's the graduate finite element class.
Oh, really?
Yeah.
Oh, wow. What's different?
We do more. So there's actually 2. So there's 540 and 541. 540 we focus mostly on ANSYS, and so compared to 410 we do some more advanced ANSYS stuff. And the class is basically all project based. Oh, 541 goes more into the theory of ANSYS. And so actually where 541 goes, it's quite similar to this class.
Really?
For 541, the final project is have you guys write your own finite element code. And for this class, we've been writing code the whole time too. So it ends up, 541 and 417 are actually similar.
Okay.
Yeah.
Is it mostly in MATLAB or?
Yeah, it's all MATLAB.
Does anyone do it in like Python or anything?
A couple people have. Yeah, I think some people have a really strong interest in learning Python, so they try to do it there. But it usually doesn't last too long because all the sample codes I give are in MATLAB, and so people don't want to convert all those to Python. So it usually only lasts for 1 or 2 assignments. All right.
Oh, really?
It's not that. I mean, I think it's not hard. I think the most difficult thing is that Python, the indexing starts at 0, and MATLAB starts at 1. And so that seems like a small thing, but when you're computing things like, like the ID equation that we have here, and you're trying to convert that in Python, that's really annoying. And so like a lot of small things like that.
Oh, I see. Yeah. It's like you're minus in one place and then Python's in
Exactly. Yeah.
All right, have a good one.
Thanks, you too. Have a good weekend.